Hello students, title of today's lecture is MOSFET mobility. So today we are going to discuss mobility of carriers in a MOSFET device. And remember that the mobility is being measured between the drain and source portion, or you can say inside the channel region of the MOSFET device. Before moving towards mobility of carriers in case of MOSFET, let's have a general discussion about the mobility. Mobility, it is the easiness with which carrier can travel into the semiconductor. And when the carriers are traveling into the semiconductor, they encounter many kind of scatterings. They may be they may face lattice scattering. There may be ionized impurity scattering, neutral impurity scattering, piezoelectric scattering, or surface scattering. All these scattering mechanisms will have certain influence on the mobility of carrier. And corresponding to all these factors, there are various different kind of mobilities defined. So the net mobility will be given by this equation. So here mu1, mu2, these are mobility values which corresponds to different scattering mechanisms. So all these are taken into account in order to find out the net mobility of carriers into the semiconductor. And remember one more thing, the smallest mobility will dominate into the total, or you can say into the net value. So now let's move towards the mobility of carriers into the MOSFET device. So here the main important term is effective mobility. So when we talk about effective mobility, so again I'm telling you that we consider this particular portion of semiconductor which is between drain and source region. You can see this structure. So this is source which is grounded, and this side is drain. Where the drain we are applying certain potential. So you can see that this potential which is applied on the drain, that is VDS, right? So the equation of current in case of a MOSFET is given by this equation. So you know very well why we are considering this equation of current for finding out mobility, because current and mobility, they are related to each other. Higher the mobility, more will be the current into the semiconductor. And this equation, you can see there are two parts in this equation. The first term is the drift current. So this part is drift, this part is drift, and the second term is diffusion current. So this part is diffusion component. You can see here diffusion component because there is a concentration gradient term here, and in this side you see in the here in this component that concentration gradient is not there. Rather you can see there is VDS, drain source voltage. So this component depends on the drain source voltage magnitude. Now most of the time we operate this device into the saturation region, but here for simplicity we will consider the case that when this drain source voltage is lower. So when this drain source voltage is lower, in that case this drift component will dominate, and this diffusion component can be ignored. So remember, this is for simplicity only. So this first component, which is the drift component, that we are going to consider in our further calculation. So if this VDS is lower, in this case this component will dominate. And if we find out the derivative of this ID with respect to VDS, so you can see here this expression, partial differentiation of ID with respect to VDS. Remember, this part is ignored now. If we differentiate this ID with respect to VDS, so what we get? We get conductance GD. This is a drain conductance, or you can say this is channel conductance, because we are talking about channel current and voltage between drain and source. So the voltage across channel, right? So this is channel conductance, and this will remain constant. Sorry. So if you find out GD from here, and you can say for that we have to differentiate ID with respect to VDS. So we get GD here, and this GD will be equal to W into mobility into Qn divided by L. And from that expression it is possible to find out mobility. So if we talk about mobility, effective mobility, so this W will get multiplied by GD, L will be multiplied here and W will come into denominator. This Qn will also go into denominator. So the effective mobility in case of MOSFET device will be given by this particular equation. So you can see here, if you want to find out effective mobility, what we need? We need L and W values, of course, GD and Qn. So out of these four components, L and W, they are design parameter. So for a given structure, these values are fixed. The GD and Qn, they are another important parameters, and we have to find out these parameters accurately if we want to estimate the mobility of carriers into the MOSFET. Now, this is the most tricky part. GD is channel conductance that we can find out using this kind of, you can see from this expression. So, if we have a ID versus VDS curve, so from the slope of that curve, it is possible to find out the channel conductance. And what about this Qn? Qn is the charge into the channel, and this charge is n-type charge because here we are considering a NMOS device. That's why this Q is Q have this N subscript here. So this is NMOS device because the carriers into this NMOS are N-type carriers, right? So this is NMOS device. Anyway, so these Qn is free charge per unit area. Means the electron density per unit area, you can say. That will be calculated with the help of this kind of equation. You can see this is very simple equation, and this equation is applicable in case of capacitors also. You know this expression in case of a capacitor, Q is equal to CV. So this simple expression is used here, right? C is the C part, V is replaced by VGS minus VT. You know this VGS minus VT is actually your overdrive voltage. Sometimes we call it VOV also. So this overdrive voltage means whatever voltage higher than threshold voltage applied to this gate terminal, that will contribute to the free electrons into the channel, right? So VGS minus VT instead of simple V is going to play important role. And this capacitive component, which should be there in this equation, that is replaced by oxide. So now you must be thinking that from this expression, it is easy to find out Qn and GD also we know how to find out. So what is so special in the measurement of effective mobility? It's a simple task, but actually it is not simple task. Why? Because you see here this Qn, it depends on many parameters. VT, VT exactly finding this VT exactly is very difficult. So the VT is not exactly known. This is one particular issue which is very important. Second thing, when we talk about this oxide capacitance, this is not strictly oxide capacitance, right? So C ox is not strictly oxide capacitance because when we measure capacitance in case of MOSFET device, so that measured value is not only oxide capacitance value, because that measured value contains many capacitive components. For example, drain overlap and source overlap, that overlap capacitance is there. And sometimes, you know, in case of MOSFET devices, the gate is made of polysilicon material. Polysilicon is a semiconductor. So when we apply a voltage on the gate terminal, some depletion occurs into polysilicon also, right? Most of the time we ignore it, but if we are interested to go for more accurate calculations, we cannot ignore that depletion capacitance. That depletion capacitance in the polysilicon material will be in series with the channel capacitance, and that way uh, the net capacitance which is measured from that experimental setup, that will not be strictly oxide capacitance. So this polysilicon capacitive component, then overlapping capacitive component, all those capacitive components are there. So because of that, it becomes very difficult to find out Qn with accuracy, because the capacitive value, capacitance value which we have from the experimental setup, that is not strictly oxide capacitance. VT is also not known accurately. And another thing is that the capacitance which we get from that setup, that capacitance is dependent on the gate voltage. So it means if we change the gate voltage, that capacitance changes. Because of so many complexities, it becomes very difficult to find out Qn, right? So in the coming slides, we are going to discuss certain ways so that we can find out the true value of capacitance, which can be used to find out the charge into the channel region. And knowing that charge with accuracy is important for finding out the accurate value of effective model. Uh, so, in order to avoid the difficulties of finding the accurate value of charge, so instead of that equation which was shown in the previous slide, we prefer to use this kind of. So here you see this equation have this gate channel capacitance here, and that is within this integration term, because we discussed that channel capacitance depends on the gate voltage also, right? So that factor is taken into account here. So the Qn is used uh, like this. So it's integration of gate channel capacitance, and the limit is the gate voltage changes from minus infinity to uh, some given value, right? So that kind of expression gives us more accurate value of free electron charge into the channel region, right? Now, how we do it? Let's start with this particular structure. So here again, remember that this is NMOS device, because this is P-type semiconductor material. So if it fabricate a NMOS device that is in P substrate, of course. So here you see this is source region, this is drain region. This drain and source, they are connected together. So that connection is not shown here in this diagram, but actually drain and sources are connected together. So here in this structure, if you see, one electrode is this gate source. So here it is shown connected to source, but actually this drain is also connected here. So drain source, they are connected together and they form one electrode. Second electrode is the gate terminal. So this is your gate terminal, right? So second electrode is your gate terminal, and first electrode is your source and drain connected together, right? Now, if the gate source voltage is less than Vt, right? Or you can say when the negative voltage is applied here. So what will happen? This VGS is negative value. What will happen in that case? The holes, free holes which are present in semiconductor, they will be attracted. Now, if we see this channel region and this drain and source region, so in drain and source region, there are N-type carriers, and in this channel, there are P-type carriers. So there is a type of P-N isolation, right? And this electrode is not connected to this channel region. Since it is not connected, so this portion and this portion, they will not interact with each other. So if we measure capacitance between these two electrodes, that capacitance is actually this overlap capacitance. Sorry. So this overlap capacitance, gate source, overlap capacitance, gate drain. So only these capacitances, so they are counted, because this portion is not connected to this electrode, right? So you can see that if this VGS is less than VT, means when the gate is connected to a very high negative potential, that time whatever capacitance which we are measuring between these two electrodes, uh, that capacitance is two times this overlap capacitance. Two times, because these two capacitive components are parallel, and since they are parallel, they are added directly, right? Now let's consider the second case when VGS is greater than VT, means when we apply positive potential. So when VGS is greater than VT, at that time uh, this gate voltage is positive gate voltage, and because of positive gate voltage, channel formation occurs within this portion. Of course, there is a depletion region, and within this depletion region, there are free electrons. So in this situation, you see a drain, source, and channel. They all are filled with a single type of charge, So they are connected together. So you can see that the channel portion is also connected through this source drain electrode. So in this situation, if we measure capacitance between this electrode and this electrode, we measure capacitance here between these two terminals. So that capacitance is collective capacitance of this overlap components and channel components. So in this case, you see here the capacitance which we have measured is 2 time overlap capacitance plus this channel capacitance. All these capacitive components are in series, so they will get added. So the total capacitance is this. Now, in the next slide, you will see that how this measurement will help us to improve accuracy in the capacitance measurement. See here, okay, yeah. Look at this graph. Here on the x-axis there is gate voltage, and here this is capacitance. So you see here, so when this capacitance was, you see here in this portion, low gate voltage was applied at that time. The capacitive, the capacitance which we got from the setup, that was 2 times overlap capacitance, and in this portion it is 2 time overlap capacitance plus channel capacitance, right? So in this portion, this high gate voltage, positive gate voltage is applied, and here the voltage was less, or maybe in some cases negative voltage. Now if we subtract this 2 COV from this entire graph, what will happen? This entire graph will move in the downward direction. So this portion will go to 0, right? Because 2 COV is subtracted from entire graph, and this will be slightly less here, right? So if we subtract 2 COV, and that 2 COV we can find out easily from this graph, we have to take reading from here, uh, where this value is, and this value we see from this graph, and we subtract this value from this entire graph, right? So that way this capacitance value will be corrected. So that overlap capacitive component, which is a parasitic capacitive component, that will be subtracted from this whole part, and what we get, that is purely channel capacitance. So that way we are able to eliminate at least one parasitic capacitive component which was present in our measurement, right? So that way you can say that a little bit accuracy can be improved, right? So now once we get this corrected value of capacitance here from this graph as a function of gate voltage, then with the help of this equation we integrate it and we find out Qn. So this graph, this is Qn, right? So this linear graph you see here, that graph is Qn, right, as a function of gate voltage, and this value we got from this, right? So you can see here this Qn charge, free carrier charge density, that is plotted here on this side of y-axis as a function of gate voltage, right? So you see Qn changes as we change the gate voltage, and in this graph you can see there is drain current plotted versus drain voltage. This is VDS actually, right? ID versus VDS, and this is for low voltage of VDS. You see here it is up to 0.1 volt. If we got higher voltage, then definitely we will get that saturation region, but we are confining ourselves to low DS, low VDS range, right? So you see here the graph is almost linear. So from the slope of this graph, right, from the slope of this graph, we can find out GD, because GD is, in the first slide you have seen, GD is differentiation of ID with respect to VD, right? So x-axis here is VDS and y-axis is ID. So it means slope of this graph can give you value of GD. So GD you can find out from this graph, Qn you can find out from this graph. So once you know Qn and GD, it is possible to find out mobility, right? So mobility you can find out from this equation. You have seen this equation, how we got this equation in the first slide. So put the value of GD here and Qn here. L and W, they are design parameters. From the structure of device you can see their value and you can find out effective mobility. Now the effective mobility is plotted here as a function of gate voltage. You know that Qn changes with the gate voltage. So you can see the mobility also changes with the gate voltage. Qn increases as you increase the gate voltage. It means effective mobility will decrease because effective mobility is inversely proportional to Q. As you increase the gate voltage, effective mobility is decreased, right? Now let's move a little bit. So so here we are going to discuss one more method for finding out the capacitance, channel capacitance. You can say that method is known as split CV measurement method. So in the split CV measurement method, what we do, we measure capacitance between drain source connection and drain source as a single electrode and gate as second electrode. And the second arrangement you see here, that is for measuring the uh, gate channel capacitance. So means one terminal is gate terminal, second terminal is channel or bulk terminal, sorry, bulk terminal, right? So you have seen in the earlier slide that when the gate and source they are connected together and suitable gate voltage is applied here, then the channel have a single conductivity and that act as one full electron, right? And that way it is possible to find out the channel capacitance. So the equation for that is given here. I1, I1 is the current which flows between drain source electrode and gate electrode. So this equation, you know, the current is flow of charge per unit time. So dqn is the charge density. So actually this I1 is dqn by dt, but this dvgs is inserted here in the numerator and then in denominator. So this part, if you see here, that is free carrier uh, charge variation with respect to gate voltage. So this term is mentioned here as Cn, or you can say as C gate channel capacitance, right? So the Qn can be obtained from I1, and I. If we talk about I2, that will be dependent on the bulk charge which is present here, and the bulk charge basically is because of the dopants which are present here, or you can say the depletion region which formed into channel region, that will contribute to I2. So I2 will be again it will be given by this equation dQB divided by dt, means rate of change of bulk charge, right? Here also in the same way this gate source voltage is inserted. So this term is your bulk capacitance because it gives you value of or you can say the variation of bulk charge with respect to gate source voltage. So this capacitance is termed as CB, bulk capacitance, or sometimes it is mentioned as gate bulk capacitance, right? So QB and substrate doping profile can be found if we use this equation. But if we use this equation, it is possible to find out gate channel capacitance. So this is another way of finding out gate channel capacitance, and we can use this gate channel capacitance into our calculation for finding out Qn. Now let's move to, okay, so this graph shows variation of gate channel capacitance as a function of gate voltage, and this is the graph of gate bulk capacitance. So when the gate voltage is varied, you see here, once we are in the positive gate voltage region, when positive gate voltage region, you know, in case of NMOS device, if gate voltage is positive, then uh, free carriers, or you can say channel formation has occurred, and there are a lot of free carriers present into the channel region. So whatever capacitance is there in the gate channel or a gate bottom between gate and bottom electrode, that capacitance will be controlled mainly by the free carriers. Free carriers will dominate. Free carriers will control the capacitance. But in case of negative gate voltage, there was no free carrier, no channel formation had occurred, and since there was no channel formation, so no free carriers were present there. So the capacitance was controlled by the immobile ions which were present there into the depletion region into semiconductor. So the immobile ions were contributing to the capacitance. So that's why this gate bulk capacitance was dominating here. But once channel formation has occurred, for example, in case of positive gate voltage, then there are a lot of free electrons. So free electrons will dominate the capacitive component, right? Now, another important point, effect of vertical electric field. When we work with a MOSFET device, so suppose this is your oxide, and here on the top there is metal, and this is your gate terminal, right? And this is your semiconductor. This is your, you can say, drain, and this is your source. So the structure is something like this, right? Now, when we apply a voltage on the gate terminal, so if it is NMOS, then we apply positive voltage. So what will happen? So there is a vertical field, right? This vertical field is present. This vertical field is something like here. It is like this, and it is because of the positive gate voltage. This vertical electric field. So what this vertical electric field will do? This will influence the mobility of carriers into the semiconductor. Reason is that they all are free electrons here, and because of this, the electrons will get attracted towards this oxide semiconductor. This is your oxide, right? So the electrons, what will happen to the electrons? So if I use a different ink here, black, now the electrons will be confined to this part, right? This part. So the electrons are present here. So if this electric field becomes strong by increasing the gate voltage, these carriers will be attracted more towards the interface. And if they go more towards the interface, there are a different kind of scattering mechanism will come into existence near the interface. Because near the interface, there are dangling bonds, and because of dangling bonds, there are many kind of impurities between the impurities trapped into those dangling bonds or those traps, and those impurities act as new scattering center. So the mobility of the carriers which are moving into the channel, that mobility decreases. So this is theoretical explanation, or you can say the conceptual explanation of effect of electric field, vertical electric field on the mobility. And I just explained that mobility decreases if the gate voltage increases. So mathematically, that relationship is given here, right? This equation gives you that relationship. So this mu naught is original, or you can say true mobility, and this effective mobility is the mobility after considering the influence of vertical electric field. So this mu naught means we are not considering the effect of vertical electric. So this alpha term is there. This alpha is constant, and this gamma is also constant. You see here. So if this vertical electric field increases, this denominator part increases, so effective mobility decreases. So from this mathematical expression also you can see that the vertical electric field, increase in vertical electric field decreases the mobility of free carriers into the channel, right? Now this electric field here, that will that the field is always because of charge separation. If we talk about charge on the gate side, that charge is because of the supplied gate voltage. If we talk about charge on the semiconductor side, charge on the semiconductor is because of two things. So this is negative charge here in the semiconductor, and that negative charge is contributed by the free electrons, Qn component is there, and by the bulk charge you can say that is because of immobile ion. So I still again I have to change the color here. So this Qb is because of free or can say immobile ions, and Qn is because of free electron, and this is a constant here. So that constant will depend on like whether it is electron or hole, and it also depends on many other factors. You see here distribution of carriers into the channel portion. So at higher gate voltage this distribution is something like this. Near the source the depth of free carriers is more, means they are distributed to long depth, but if we go near drain the depth becomes less, and sometimes the depth is zero because the free carriers are not present near the drain part, right? So that distribution uh, is taken into account by this component, and the type of carriers, whether the electrons are present into the channel or holes are present, they are also taken into account by this parameter. So this parameter is half if we are considering the electron uh, free electrons into channel region, for example for NMOS. But if we are working with PMOS, then hole are moving inside the channel. So in that case, the value of this parameter is 1 by, right? So this is you can say the dielectric constant of semiconductor epsilon naught. Its primitivity, or its yeah yeah. Now here if you see in this equation, this effective mobility. So this equation is for n-type semiconductor, right? So the constants are inserted here at 638 divided by 1 plus this vertical electric field divided by 7 into 10 to power 5, and this power is this gamma is 1.69, right? So all these constant values are inserted here. So this equation is more easy to use and more quick to use, you can say, right? And if we are talking about a PMOS device, then the mobility of p-type carriers into that PMOS device, that will be given by this equation. So here also constants are inserted here. The mobility of holes is less, so this part, that's why this value is less as compared to this value. And the constant this alpha is also inserted here, and gamma here is not shown. It means the gamma is 1 here, right? So from this slide you have seen that how the effective mobility depends on vertical electric field. So all these were theoretical calculations or theoretical considerations, but practically if we study the effect of vertical electric field, so you can see here this uh, data is shown here. So how this mobility, effective mobility in case of NMOS devices varies with the effective vertical electric. And in this graph, the variation of mobility in case of PMOS device is shown as a function of effective, right? I was talking about experimental data or experimental behavior of mobility as a function of gate voltage. So in that earlier equation where we are discussing that theoretical equation, so electric field was given, but practically when we use a device, when we perform some experiment, so it becomes very difficult to find out the electric field because we need to know various dimensions, film thicknesses, etc. So it is more handy or more easy to use voltage as a parameter into that equation. So the equation which is more handy, you can say, that is shown here. So it becomes more easy to use this equation when we perform experiment. So here instead of electric field, the gate voltage, or it's not gate voltage, actually it is overdrive voltage, means the gate voltage higher than Vt, Vgs minus Vt is given. Theta is a constant, that is a parameter. The theta is mentioned here, that is called mobility degradation, and this mu naught is like mobility of electrons or holes into the semiconductor. So this this mu naught, that is intercept of this curve. You can see here, if VGS minus VT gate voltage is changed, so this mobility, effective mobility is plotted here, right? So this mu naught is this particular, right? Now, if you talk about this theta, theta is actually slope of this graph. So if you normalize this graph like this, you plot mu naught divided by mu effective. So what it becomes? It becomes like 1 plus theta VGS minus VT, that becomes equal to mu naught divided by mu effect. So if you manipulate mathematically this equation, we reach to this kind of formula, right? Right. So this, you can see this equation is just like the equation of straight line. This is y, this is m, x, and this is one, this is c, right? So if you compare this, so here you see on the y-axis we have this parameter y naught divided by y effective, and on the x-axis we have this VGS minus VT, right? So this equation is equation of straight line. So theta, what is this theta? Theta is your m, means slope. So from the slope of this line, you can find out value of theta and you can insert this value of theta, right? And if you plot graph like this, you can find mu naught from mu naught is this, right? When VGS minus VT is 0, we put this value 0 here, this term will vanish. So what you get, effective mobility is equal to mu naught. So this effective mobility is equal to mu naught. By putting this VGS minus VT 0 here, you can see this effective mobility is equal to this. It means this intercept is your mu naught. So these two graphs you have to plot. So from this graph you will find mu naught. From this graph you will find theta, and then you can put these constants here, and then you have a mathematical relationship which is more easy or more quick to use, because this equation gives you variation of effective mobility as a function of gate voltage, not as a function of electric, right? So that is more easy to use during experiment. So I hope that most of the concepts which are covered today, they are clear to you. Now you know that how to measure effective mobility in case of MOSFET devices. The value of GD, channel conductance, and uh, channel charge Qn in case of NMOS device, that Qn. These two parameters you should know very well. Finding Qn is a challenge because you don't know this oxide capacitance accurately. So whatever capacitance you are measuring from the device, that capacitance have many other components. It becomes very easy to separate out other components to get the value of oxide capacitance. And if you don't know accurate value of oxide capacitance, there are chances of error. So we have discussed certain mechanisms in which you can isolate the oxide capacitance from the from the other parasitic component, right? And we have seen the effect of vertical electric field on the channel conductivity. You can say the increase in the gate voltage or increase in the vertical electric field decreases the mobility of the carrier. In the next lecture, we will see many other factors in case of MOSFET device or in case of MOSFET structure, which affect the mobility of carriers to the channel, right? So till then, bye bye.